Okay, well,
Um,
yes.
Small question, in our definition of the fundamental theorem of arithmetic, we limited that to greater than or equal to 2. Is there a specific reason we can't use one, just one for that?
Because one is not prime, right? So one itself is not, can't be written as a product of prime. That's a good question, right? The statement that Min is saying about the fundamental theorem of arithmetic, correct me if I'm wrong, is if you have a natural number that is greater than or equal to 2, it can be written as a product of primes uniquely, right? One itself cannot be written as a product of primes because one itself is not prime. And actually, there's a more general statement of the fundamental theorem of arithmetic that says if you have any integer that's not 0 plus or minus 1, it can be written almost uniquely as a factor, as a product of primes, but the only ambiguity is whether or not the sign, right? So you might factor 6 as 2 times 3, or you might say minus 2 times minus 3, and so. Okay, other questions? Other questions? Okay, well, let's welcome to okay, so this is the first bit. Really, we're getting into the abstract algebra part. What is a group? Well, I'll give you kind of the elevator pitch real quick. What it is it's a non-empty set, so it's some stuff, but it's not just any set. There's a magic way that I can take any two elements of the set and combine them and get a new element of the set. We give you an example. The integers, right? Just take the ordinary integers. What happens when I take two integers and say add them up? Right? 2 plus 5. Do I get a donkey? No, I get another integer, right? 2 plus 5, 7. No matter what two integers I add up, I get another integer, right? Now, groups are basically a collection of elements where you have an operation, you combine them, and it's still in the set. And you also have some other things. You have an identity element, and you have inverses. These are very important in the study of symmetry, among many other things. And although at the beginning it might look like, oh, this is some bored mathematician contemplating his or her own navel, right? Some abstract nonsense. It actually has lots of applications. In fact, in my undergraduate school, if you were a chemistry major, you didn't have to take abstract algebra, but you had to have a little bit of group theory because they studied symmetries and like basically crystals and things of this nature. So to warm this up, let me first tell you, give you a definition here, something I'm going to call a binary operation. Let's let G be a non-empty set for starts. A binary relation which at the beginning, I'll put a little circle here. This is my relation. On the non-empty set G, this is just a function. P cross G and G. So in my notation, if X and Y are in G, then X circle Y is in G. So you take X and Y into the two coordinates of this function, and X circle Y spits out as in G. That's what a binary relation is. It's just a function on the set G is a function from G cross G to itself. We say this relation is associative if for all X, Y, and Z, in the set G, X circle Y circle G is X circle Y circle Z. B, how many of you have ever seen associativity before, right? You've probably seen that in a buzzword. We say this operation circle is commutative if, anybody know what this one is for all X, Y, and G?
Circle Y is equal to Y circle X.
That's correct. Commutative means it doesn't matter which order that you put these things together. You get the same answer, you get the same outcome. So here are some examples. How about some examples of a binary operation? Right? Because in this case, something like 5 circle 6 is 5 plus 6, which is 11. And I don't know much, but I know that that's an integer, right? Integer addition is associative, right? I mean, nobody would bother to do math if I would. It would be a disaster, right? But 5 plus 6 plus 1 is 5 plus 6 plus 1, right? So we've got associativity there as well. So this is associative. And this one's commutative as well, right? Anybody think of another binary operation on this?
Multiplication.
Multiplication is also a binary operation, right? And it's associative and commutative. All right, all right. Can somebody give me an example of a binary operation? I think you're probably going to want a different set, but give me a set with a binary operation that is associative, but not commutative.
Subtraction. Subtraction of the integers.
I think you might have associativity problems with that one. Yes.
Matrix multiplication.
How about matrix multiplication? Let by two matrices. I know that you all are probably still, overcoming the scars of linear algebra, right? But you do remember in linear algebra, when you multiply matrices, it's associative, right? A times B times C is the same thing as A times B times C if you have 3 square matrices of the same size, right? Everybody okay with that? So this is associative, but it's not necessarily commutative, right? Three, 0, minus 1, 2. This matrix is 2, 2, 5, 2. Right, when I do it in that order. And if I do it in the other order, well, it's already different. 3, 3, 3, 1. So notice here, my binary operation, although associative, order matters. Everybody okay with it? Here's another one. Anybody think of a binary operation on the Rubik's Cube? Well, my operation is just going to be turning things, right? Any scramble you want. So for example, I might call this scramble X and this one Y. Right? What I'm doing with my hands is I'm just kind of moving the sides around. Corner pieces go to corner pieces, sides go to sides. It's a function that I'm doing by moving this around. So when I do it a couple of times, it's function composition. So this is an associative operation, but this is why the cube is hard to solve. How many of you can solve one of these? Anybody? It's not everybody. In fact, almost nobody. X, Y, that's what that looks like. Other order, YX, that's what it looks like. So order of this matters, which is one of the reasons it's hard to solve. So that's yet another example. Okay, any questions? Okay. Now, let me give you a definition of what a group is. And then I am going to spend quite a bit of time looking over a lot of examples. We're going to look at a lot of examples of groups because what we're going to do in the abstract setting will generalize a lot of these examples. And I think it's good to have kind of a toolkit of some examples that you can kind of call to mind to help you out with this. Right? So, definition 213. A non-empty set G is called a group if G is equipped with a binary operation so you've got a binary operation from G cross G into G, such that I'm going to call the first one 0. My first property 0, because this one is redundant, but I like to do it anyway. And sometimes when considered from this respect, this is called closure, right? I really don't need to say this because this is subsumed in the fact that G is equipped with a binary operation, right? So the binary operation means this, but sometimes this is called closure property. When I take two elements of the group and combine them, they're still in the group. Number one, X So this just means the second, number one just means that that the operation is associative, right? So my binary operation is associative. Now I want two other groovy things to help me out. Number two, there exists E and G. There's some magic element of G that has the following property, such that E combined with X in either order is X. E is called the identity element or sometimes the neutral element. It is the one that you can combine on either side with any element of X and it leaves it alone. Gives it the same output that you had in. And three, this is sort of the untying. This goes in with the identity. There's always, given any element, you can always kind of untie it to the identity. That is, for all Y in G, there exists X in G, such that X combined with Y combined with X is equal to the identity. This is called existence. So X is often called the inverse of Y, and it's what they expect. Would everybody agree that no matter what mess I do to this Rubik's Cube, so I do this to it, you fix it? Maybe not, right? But can you theoretically fix it? Would you agree that if I'm clever enough, I can get back to the pristine solved Rubik's Cube, right? That's what you're telling me right there. Given any Y, that's the scramble that I did on the group on this, you can find some X that puts it back to its original state. By the way, can anybody tell me how to do it? I mean, what I could do? One of the things that you could do is you could keep a Rubik's Cube diary, turn this, and this. To undo it, just do everything you did in reverse in the opposite order, right? And that's what you'll get back to it. So if I kept a Rubik's Cube diary for that mess that I made, which I didn't, just running it backwards in reverse will get me back where I started. I agree with that. Okay, so this is what a group is. It is just a set, not empty, equipped with some operations such that if I give you any two elements of that group and you combine them, you're in the group, right? This way to combine them is associative. There exists an identity that leaves everything alone. And given anything in the group, there's something that takes it back to the identity. You combine it back to the identity. So the first thing to do is do some quick examples, and then a couple theorems, and then we're going to beat the examples to death. Any questions so far, though? Okay, how about some simple examples? Can anybody think of an example of a group? So here's some kind of first examples.
Integers.
Okay, I like that. But if you're going to tell me the integers, I'm going to have to say, what's the operation?
Multiplication.
Okay, what if we do the integers under multiplication? Let's check our facts. Is it true that when we multiply any two integers, we get an integer? Ding, 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 we're there. Okay, so we got that covered. Is multiplication of integers associative? You bet it is. What's the identity of multiplication of the integers? What integer can you multiply by any integer and it leaves it alone? 1. Everybody agree with that? Oh, no matter what, we're doing better than meatloaf. We got 3 out of 4. How about the last one? What's that? Uh-oh. This one's a problem for the integers under multiplication. Can anybody tell me why? I'm sorry?
Fraction sign.
Right. Suppose I give you the integer 2, right? Well, what do you multiply 2 by to get the identity, which is, you said 1. You got to multiply by 1/2. Everybody agree with that? Is 1/2 an integer? Newman. So this doesn't quite work. But this is a group, right? Because when you add 2 integers, it's an integer. Addition is associative. What's the identity for adding the integers? 0. 0 is the integer that leaves everything alone. And what is the inverse of an integer under addition? What's the inverse of 7? -7, right? It's just the minus sign. And the minus sign of any integer is still an integer. Everybody agree with that? So this one's good to go. Okay. I'd really like to repair this though, right? Yes.
The real numbers under multiplication.
Right, maybe you could go to the rational with the real number, okay? Would everybody agree that the real number's under multiplication? When you multiply two reals, it's a real, right? Multiplication of reals is associative. The identity is one again, under multiplication. Do I agree with that? What about this? Almost. What's wrong with? You still don't have inverses always. There's one defect. What is it? 0. 0 is a problem. Brayden, you want to fix it?
Real numbers minus 0.
How about this? This is a group. If you just toss the 0, now everything has an inverse, right? Because if you have a non-zero real number alpha, its inverse is 1 over alpha, which is also a real number. The only reason you were hosed before is because there is no 1 over 0, right? Everybody okay with it? Okay, how about some other examples? You know, we've come up with this example and this example. Let me give you some more. The rational numbers under addition, the real numbers under addition, complex numbers under addition, all groups. The rational numbers, throw out 0 under multiplication, agree. All of these examples have two things in common. One of them is all the groups are infinite. Everybody agree with that? Another one is all the groups, the operation is commutative. Everybody agree with that? Order doesn't matter in any of these examples. Can anybody give me an example where the order does matter? Here's this is one. Again, I'm going to pull this out of linear algebra. Well, actually, before I do this, let me do a preliminary. So, this notation will mean 2 by 2 matrices with coefficients real. So this is a set of matrices that look like this. And under addition. What happens when I add up two 2 by 2 matrices? What do I get? Another 2 by 2 matrix. Everybody agree with that? Addition of matrices is associative. We've seen that actually in 3110. What's the identity matrix here under addition? It's the matrix that's all zeros. Everybody agree with that? So there's your identity. And if I give you the matrix A, B, C, D, what is its additive inverse? Just put negatives everywhere. Negative A, negative B, negative C, negative, right? Okay, so this one's a group. Right? Does order matter here? That doesn't matter what order you add matrices. But I do remember the matrix multiplication, that order does matter there. So how about this? Anybody want to take a guess for a good group we could get out of this? We can't use all of these, right? Because if I'm multiplying matrices, let's suppose I multiply 2 by 2 matrices. What's the identity for 2 by 2 matrices? the two by two identity is what? 1, 0, 0, 1, right? Everybody agree with that? Okay. What two by two matrices have inverses? Can anybody determine the answer? They have an inverse if the determinant is not 0. Do I agree with that? So let's try this. Okay, so I'm gonna find this. This is A, B, C, D are real, but I've got an extra caveat, and that is AD minus BC is not 0. So that means non-zero determinant. Are you okay with it? Okay, let's think about this. What happens if you multiply two matrices, 2 by 2 matrices? We get a 2 by 2 matrix, right? But then AB is 2 by 2, 2 by 2 matrix. Or for it still to live in GL2R, it's got to have a non-zero determinant, right? Does it? Yes, it does. Do y'all remember from linear algebra, the determinant of A times B is the determinant of A times the determinant of B, right? So if we look at that here, that's an old friend from linear algebra. So if both of these are not 0, then this is not 0. Right? So in other words, if you multiply two elements of this set, it's still in the set, right? So it's a good candidate for a group. We know that the multiplication is associative. The identity is 1, 0, 0, 1. What's the determinant of that matrix? It's 1, right? And so it's in there too. So we've got the identity matrix. Any matrix that has a non-zero determinant has an inverse. That's a linear algebra thing. So this is actually a group. But this is group, but binary operation is not commutative. But this group is also infinite. Everybody agree with that? This is an infinite group. Can anybody give me an example of a group that's finite? So that would be something new. So a group that doesn't have many elements. Any ideas? While you cogitate that, let me give you the definition that I'm quite sure is coming up later, but I need to tell it to you now, I guess. Definition. If E is a group and XY equals YX, that is, if the binary operation is commutative, then we say G Abelian. So if I ever say the word to you, an abelian group, which I will, that just means a group where the order doesn't matter, like the integers under addition, something like that, where when you combine X and Y, it doesn't matter what it is. Okay. How about a finite? That is? Yes.
Is that under addition or multiplication?
Yeah. You have to be careful with the multiplication and make sure it's right, because for example, in Z6, you might have 2 doesn't have an inverse, but you can get around that. Let me start this way. I was hoping you would actually say that. Well, actually, now that I think about it, let me start off with a smart example. Just take the number 0 out of the integers. Just 0 by itself under addition. And I feel like a complete tool, right? Because yes, when I add 0 and 0, I get 0. And is it associative? I'm adding the same thing. But nonetheless, this is a group, right? And by the same principle, 1 under multiplication is a group, right? Here under addition, 0 is its own inverse, right? Under multiplication, 1 is its own inverse. So, okay, there's a finite group, but that's boring, right? But there is a takeaway from this. And the takeaway is the identity is always a group, right? If you just take the identity itself from the group. Now here's a better example that was just suggested to me. This is a finite group because there's only finitely many things in it. So for an example within the example, you remember how we talked last time about how to add this, right? 2 bar plus 2 bar is 4 bar. You just add them up like the ordinary integers. And if you exceed 5, you just divide by 5 and take the remainder, right? So 4 plus 4 is 8. Oh dear, 8's too big. 8 divided by 5 goes in 1 with remainder 3. So 4 bar plus 4 bar is 3 bar. Am I okay with that? That rule gives you a closed associative operation. Everybody cool so far? What's the identity here? What can you add to anything and it leaves it alone? Yes, and of course this is under addition. The 0 bar leaves everything alone. Agreed? And I can tell you what everything's inverse are, right? 0 bar is its own inverse. That's always true for the identity. 1 bar and 4 bar are inverses because they add up to 0 bar. And 2 bar and 3 bar are their own inverses. Okay? Everybody okay with that? Okay, we've covered about everything. The only thing that I've kind of left out is, can anybody give me an example of a finite group that is not abelian, that is, order does matter? Oh, we're going to see a bunch of these for sure. But here's a familiar one. Or one that we can visualize. Take a Rubik's Cube, right? Now, my group is going to be the rearrangements on a Rubik's Cube, right? So this rearrangement corresponds to the function of me turning this 90 degrees, whichever way I did, counterclockwise. This arrangement corresponds to this. So it's sort of like my hands are doing a function to this by scrambling it, right? Let me ask you this. Let's kind of go through the group stuff. What happens if I take a cube and I scramble it, I do some magic to it, and then I scramble it some more? What do I get? A new scramble, right? So one scramble composed with another scramble is a longer scramble. Everybody agree with that? Is the scrambling associative? Yes, because in 3190, function composition is associative, and that's essentially what this is it's a function composition. What's the identity? Here, let me show it to you. Here's what you do. Don't touch it, right? That's the function where you don't do anything to it at all, right? Everybody okay with that? And does every rearrangement on the Rubik's Cube have an inverse? Sure. Otherwise, they wouldn't give you the little solutions manual when you get it in the box or whatever. Again, if your kid brother took it and scrambled it and you kept a cube diary, you could go through everything did, running it backwards and reverse, and you get back. So everything has an inverse. This is a good example of a group. It's finite. Why is it finite? Well, imagine this. What we're talking about is the rearrangements on a Rubik's Cube, and there's a lot of them, but not infinitely many, right? Imagine that I took this Rubik's Cube apart with a screwdriver, which, by the way, if you want to cheat on the Rubik's Cube, it's the best way to do it. But imagine you pop it apart with a screwdriver and you put it back together. Each of these, what I call corner pieces that have 3 colors on them, there's only 8 places you can put them, right? Do I agree with that? There's only 8 corners on this. Only 8 places. And once you decide where to put it in, you can only put it in 3 ways. The yellow could be on top, or green, or orange, right? And these pieces right here that only have 2 colors, there's only 12 slots to put those in. So there's only 12 ways to put those in. And each time you put one in, you can put it in one of 2 ways. Now, this actually comes to a big number, but it's finite. And as we said before, XY gives you that, and YX gives you that. So this is the example of a group that is finite, but not abelian. So we'll order it up. Okay, any questions on that? Questions? Okay, some people say that groups are the study of symmetry, and we're going to see why people would say that in our study of groups. So let's kind of break in with a first sort of theory about groups and see if we can kind of get through it. Theorem 215. That G the so here are some properties that it enjoys for A. The identity is unique. Okay, one of the things we know about groups is it has an identity, right? That's we demand that by definition. But you might say, well, can a group have more than one identity? The answer is no. There's only one. B. For all A and G, A inverse is unique. So again, this is another one in the definition of groups. We demanded that every element have an inverse, but if it's a group, you can only have one of them. For all A and G, anybody want to guess what that is? That right. Good heavens, I hope that's the case. And number D, I don't want to guess what this one is. If you struggle with this, you might think about linear algebra. That might help you a little bit. Very good. This is just like the matrix thing that you had in linear algebra. It's the inverses of A and B in the other order. How many of you, your reflex, come on, be honest with you, your reflex is to write A inverse, B inverse here. How many, right? Come on, everybody wants to, right? We all want to, but you can't in general because the group might not be abelian. If, however, A times B and B times A, if it's the same, then yes, this is A inverse, B inverse, but you need the elements A and B to commute. Okay, so let's prove this. We're going to go through this step by step. Let's look at A. Okay. Suppose E and F are identities. Or G. Now, of course, my theorem here says that the identity is supposed to be unique. So I want to prove that E and F have to be the same thing. Everybody agree with that? Okay, so let's write this down. E is E times F. Why? Because F is an identity. Everybody agree with that? But on the other hand, E is an identity. This is because F is an identity. But this is equal to F. And this is because E is an identity. So E and F are the same thing. Don't you feel a little dirty? I feel like I got to take a shower, like I sort of got away with something that I shouldn't have here, right? But everybody understand this? So the notion of identity is kind of a powerful one. Okay. Now I want to show that if you have an inverse, that it is also unique. So let's suppose A has X and Y as inverses. Suppose that A has both X. So what this means is AX equals XA equals the identity, and AY equals YA equals the identity. Notice that I've stopped writing the little circle in there at the same time. When I use juxtaposition like that, then that means that it's the operation. So let Y, well, Y is YE because E is the identity, right? And I can replace E with AX, right? Everybody agree with that? Y is Y times the identity, but E is the same thing as AX. Agree? Now, I'm going to muck around with these parentheses a little bit because the group's associative. This is the same thing as YA times X, right? Well, what is YA? YA is also the identity. So Y and X are the same. Short, elegant, to the point. Right? How about the rest of this? The next claim is A inverse inverse equals A. Okay. Let's give that a shot. See. Well, I'm going to write something down here. Notice that A you know that if A is in G, then A inverse times A Doesn't matter what order is the identity, because we define that to be true in a group, right? So this means, if you study this equation for a minute, this means that, so A is functioning as an inverse for A inverse, right? Because don't look at this from the perspective of A, which is where we started. Look at it from the perspective of A inverse. Here's all A inverse minding his own business. A inverse gets hit on the right by A inverse gets hit on left by A, and it gives E. That means that A is functioning as an inverse to A inverse. Everybody agree with that? But inverses are unique. By B. So the inverse of A inverse has to be A. Everybody agree with that? There's a similar thing for this multiplication here. Notice that in part D, notice that what happens when I multiply AB times this animal? Well, this is A B inverse A inverse, which is A inverse, which equals E. Everybody okay with it? On the other hand, B inverse A inverse times AB is B inverse A inverse A B, which is B inverse B, which is E. I agree. So what we've proved in this is that B inverse A inverse is an inverse for AB. Right? Because when I multiply B inverse A inverse on either side of AB, I get the identity. So AB inverse, because of the uniqueness of inverses, is B inverse A inverse. Okay. Any questions on that? Any questions? All right. I'm going to give you one last definition and we'll close
Yeah, I have
next
a-
time.
One question.
Oh, I'm sorry. Yes.
For C, if that was a homework or exam problem, would you require us to write the second line of your proof? Inverses are unique, or is that kind of implied by definition of
Oh,
inverse?
Well, I'll talk to you about test taking strategy. On the homework, you should probably be as complete as possible. On the tests, I tend to give a little bit of latitude because I know you guys are in a hurry sort of thing, but just be as complete as possible. So here's a short definition that I will end with, and that is the following states. If G is a group, the order of G is this. The cardinality of the underlying set. So for example, Z5, the order of that is 5 because it's got 5 elements in it. That's it. The order of the integers is infinite because there's infinite. And that's a good place to stop. Any questions? Questions? All right, y'all have a good one. Don't forget, I've got a skedaddle from my office. I was like one today because I got a cover a class with somebody. So let me know if that's a problem and figure something else out.